The paper delves into the concept of weak values in quantum systems, focusing on the precision and accuracy of weak value measurements in an IBM quantum system. Weak values are complex numbers associated with an operator, an initial state, and a final state, defined as the ratio of the inner product of the final state, operator, and initial state to the inner product of the final and initial states. The term weak originates from the context of weak measurements, which involve a coupling between the system and a pointer, represented by the Hamiltonian h_int equals ga_s circled times b_p. The strength of the measurement is quantified by the parameter epsilon, which determines the shift in the pointer's position. In the context of von Neumann's model of quantum measurements, a strong measurement occurs when the pointer wave packets do not overlap, allowing for an unambiguous reading of the measured eigenvalue. Conversely, a weak measurement occurs when the pointer wave packets overlap, making it difficult to correlate the pointer's position with a single eigenvalue. The authors derive the system pointer state after the interaction, which becomes a superposition of eigenstates of A_s coupled to Gaussian states centered at x equals epsilon in, each with spread sigma. They also show that immediately after a weak measurement, the evolved state can be projected onto a final system state, yielding the unnormalized final pointer state. The final pointer state is approximated using the evolution operator of a weak measurement, which can be expanded up to second order in epsilon. Under suitable weakness conditions, the truncated sum can be rewritten as an exponential. In quantum mechanics, weak values play a crucial role, and their measurement is a topic of ongoing research. This study focuses on the approximation of a state, Fp, achieved through an inverse Fourier transform, resulting in a Gaussian centered at the complex number epsilon as W. This approximation is essential for understanding weak values without relying on weak measurements. The experimental context is based on IBM's quantum platform, a versatile tool for testing quantum proposals. This platform utilizes superconducting transmon qubits, which are susceptible to environmental effects and gate execution errors. Despite these limitations, the platform enables a wide range of experiments, including tests of Merman inequalities, quantum error correction, and fault-tolerant quantum computation. The paper's primary contribution is a proposal for measuring weak values of Pauli spin operators sigma n, where n is a real unit vector. This proposal is implemented in both optical and quantum computational settings. The results demonstrate that strong measurements are not universally superior to weak measurements, and highlight the usefulness of cloud-based quantum computation devices for experimental tests. By exploring the relationship between interaction strength and measurement precision, the authors challenge previous assumptions about the optimal conditions for weak value measurements. This study presents a novel approach to measuring weak values, leveraging the capabilities of IBM's quantum platform. In the realm of quantum systems, weak value measurements have garnered significant attention for their potential to reveal intricate details about system operators. This section delves into the measurement of a system operator sigma A_n on two interacting qubits, A and B, utilizing an evolution operator U, E, that encapsulates the measurement process. By rewriting this operator in a closed form, the authors facilitate a comprehensive analysis of the weak value measurement protocol. The protocol commences with the preparation of a preselection state, I, and a pointer state, bi, followed by the application of the evolution operator and a post-selection measurement. Through this process, the authors derive an expression for the weak value, denoted as sigma A_nW, which is a complex number comprising real, R, and imaginary, I, parts. To correlate the weak value with measurable quantities, the authors introduce a set of equations involving intensities I_0, 5. These intensities are functions of the overlap between the preselection and post-selection states, the strength of the measurement E, and the weak value itself. By solving these equations, the authors obtain the squared magnitude, real part, and imaginary part of the weak value, revealing periodicity in E with a period of pi. Notably, the values E equals 0, pi, 2, and pi are identified as exceptional cases, warranting further discussion in subsequent sections. An all-optical realization of the weak value measurement protocol is also proposed, leveraging a Mach-Zehnder-type interferometer where qubits represent the polarization and propagation direction of light. This setup involves applying a transformation operator V to the incoming light on the horizontal path, while the vertical path remains unaffected. The authors describe an experimental setup for measuring weak values in a Mach-Zehnder type interferometer. The setup consists of a 50-50 beam splitter, mirrors, and unitary operators V0, V1, and Vf, which are realized using quarter-wave and half-wave plates. The evolution operator U, epsilon, is given by equation 15, which is a sequence of these plates with specific angles. The initial and final system pointer states can be implemented using similar interferometric arrangements at the input and output ports of the interferometer. The authors also propose a quantum computational realization of the proposal. They consider a Pauli spin operator and decompose the evolution operator U, epsilon, into a product of rotations, given by equation 16. The quantum circuit for measuring the weak value of sigma an is shown in Fig. 2, which prepares the initial state, I, by and applies U, epsilon, on it. The system state is prepared as the desired preselection state by applying a rotation ride to the state, 0a, while the pointer state is set to the auxiliary state, by equals, plus b equals h, 0b. The evolution operator U, epsilon, is realized in the quantum circuit by applying a sequence of rotations and controlled Rye gates. The authors then discuss how to optimize the number of gates employed in the circuit by regrouping the exponentials in equation 16. They define a controlled Rye gate, Cry, theta, which applies a rotation on qubit A depending on the state of qubit B. The evolution operator first subjects qubit A to the rotation Rz, phi, then applies the controlled Rye gate, and finally acts on A with Rz, phi. To project the evolved state onto AF, BF, the authors choose the post-selection state, AF equals 0a and apply different gates G on qubit B to select the different BF. The observables I0, 1, 2, 3, 4, 5 are measured by applying a Hadamard gate to qubit B and projecting onto specific states. In this paper, the authors report on the experimental realization of a quantum weak measurement on a 2-qubit system using IBM's open access quantum system, IBM Oslo. Their aim is to characterize the preselection state's parameters by employing 3 different circuits that measure either I0 and I1, I2 and I3, or I4 and I5. These measurements are repeated 20 times for each value of E and phi sampled, with the goal of comparing experimental results to theoretical predictions. Theoretical intensities are denoted as I0t, I5t, derived from EQs. 12. With AF, I, 2 right pointing arrow cos squared, alpha I, 2, I right pointing arrow it, and R right pointing arrow RT. Experimental mean values of these parameters are denoted as ERM and IM, with associated standard deviations sigma I0, sigma I5. The authors also provide uncertainty measures for the experimental weak values using propagation formulae, given in EQs 30a and 30b. The paper further explains how to introduce a relative phase shift of pi, 2 between 0b and 1b through the application of S. It then defines the normalization factor nu, which is theoretically expressed as square root 2 cos alpha I, 2, and experimentally determined using EQs 29a, 29b, and 29c. The results section outlines the experimental setup and procedures used to obtain the data, including the average T1 and T2 times for qubits 0 and 1. The paper concludes by emphasizing the importance of comparing experimental outcomes to theoretical predictions, which is the primary focus of this study. The research paper examines the concept of weak values in quantum mechanics, focusing on the measurement strength's impact on these values. Experimental results from IBM Oslo are presented, measuring weak values as functions of rotation angle phi for 12 different measurement strengths E. The analysis of the real and imaginary parts of the weak value, R and I, in Figure 3 shows fluctuations around 0 with increased dispersion and error for smaller measurement strengths. The paper introduces figures of merit to assess precision and accuracy, including the root mean square, RMS, value of sample uncertainties, sigma micro, and the RMS value of the difference between theoretical and experimental parameters, increment micro. These parameters quantify statistical uncertainty and systematic errors in the data. As measurement strengths increase, experimental results start to deviate from theoretical predictions, attributed to the subtraction of two very close numbers and division by sin, 2e, which tends to 0. This deviation indicates potential limitations in the measurement process and highlights the need for further investigation into the relationship between measurement strength and weak values in quantum mechanics. The section presented discusses the statistical uncertainty and systematic errors associated with measuring the weak value of sigma A, utilizing quantum computational tools hosted by IBM. The results demonstrate that the model works as expected, with statistical uncertainty and systematic errors not decreasing monotonically with increasing measurement strength. Figures 4 and 5 illustrate the logarithmic plots of statistical uncertainty and systematic errors, respectively, as functions of measurement strength. The analysis suggests critical values in the strong coupling regime where precision and accuracy behave similarly to those in the weak coupling regime. The findings confirm predictions made by equations, emphasizing the importance of choosing appropriate measurement strength to minimize uncertainties and errors. This work extends previous research by Denkmayr et al., providing experimental evidence for the non-monotonic behavior of precision and accuracy with measurement strength. The figure presents the statistical uncertainty and systematic error of the normalization factor nu, amplitude angle alpha, and phase phi as functions of the measurement strength E. The top row shows the statistical uncertainty, quantified by lane, sigma, while the bottom row displays the systematic error, quantified by lane, delta. Vertical dotted lines represent E equals pi, 24 and pi, 4, analyzed by Denkmayr et al., 8. The model's performance in different experimental contexts and its comparison to standard tomography remain open questions. The authors acknowledge the use of IBM quantum services and express gratitude for funding by FONDECYT through Grant 2,360,2015. Quantum computing research focuses on various aspects, including weak measurements and their applications. Studies by Valloni and Dequil, Das and Arvind, and Gross et al. Emphasize the importance of weak measurements for quantum tomography. The IBM Quantum Guide to Superconducting Qubits also highlights the role of weak values in strong measurements, as discussed by Zela. Direct measurement of quantum wave functions by Lundin et al., and comparisons between direct state measurement and tomography by Massoni and Rusconi are also crucial. Preliminary tests on IBM's quantum systems demonstrate the need for precise parameter settings to achieve meaningful measurement outcomes.